Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about carry look ahead adder. So in our previous session, we have discussed about triple carry adder where we have seen the carry of one stage was going to the carry of next stage was feeding to the carry stage 2. Okay, so the carry of one stage was feeding to the next stage. So here the carry was rippling from one stage to another stage, so there was a problem of propagation delay in the case of ripple carry adder. Okay, so in the case of carry look ahead adder, so let us start with the discussion of carry look ahead adder. Okay, so in the case of carry look ahead adder, this particular problem is being resolved. Okay, so here in this case of carry look ahead adder, there is no dependency upon the previous stage carry, so each stage is independent of another stage. The carry input at any stage of the adder is independent of the carry bits generated at the independent stages. Here the output of any stage is dependent only on the bits which are added in the previous stage and the carry input provided at the beginning stage. That's it. Okay, so here the circuit at any stage does not have to wait for the generation of carry bit from the previous stage, and the carry bit can be evaluated at any instance of time. Now let us see the diagram for this particular carry look ahead adder. So let us see a 4-bit carry look ahead adder, 4-bit CLA. Let us try to analyze this 4-bit CLA. So for this 4-bit CLA, we have 4 full adders. Let us say this is full adder FA4, FA3, this is full adder 3, and this is FA2, and this is FA1. So these are my 4 full adders, and for this 4 full adders, let me give the inputs. So for full adder 1, my inputs are A1 comma B1 and C1. Okay, and for full adder 2, my inputs are A2, B2, and here the carry we will see for how we are getting the carry A3, B3, and A4 and B4. And for full adder 1, my outputs are C1 and S1, C2, S2, C3 and S3, and carry 4, C4 and S4. So these are my outputs of every stage. And here in this case of 4-bit CLA, let me erase this. So in the case of this 4-bit in the case of this 4-bit CLA, my carry, the logic for my carry, for generating my carry, there will be 3 combinational circuits. So these are my 3 combinational circuits: CC1, CC2, CC3. So these are my 3 combinational circuits from which the carry will be generated. So here C1 will be generated, and C2 will be generated, and C3 will be generated to here. And for this combinational circuits, my inputs are here. For this first combinational circuit, my inputs are A0, B0, and C0. And for my second combinational circuit, my inputs are A0, B0, A1, B1, and C2. And here we will get C0 as my input, and here here also C0, not C2, and here A0, B0, A1, B1, A2, B2, and one more input is C0. And if you observe carefully, for all the combinational circuits, my inputs are the present stage inputs and the previous stage inputs, that is A0, B1, and A1, B1, A0, B0. Okay, and here also A0, B0, A1, B1, A2, B2. So for my combinational circuit 1, my inputs are A naught, B naught, and C naught. And for my combinational circuit 2, if you carefully observe, my inputs are A naught, B naught, A1, B1, and C naught. And for my combinational circuit 3, my inputs are A naught, B naught, A1, B1, A2, B2, and C naught. If you observe carefully, I am just taking the input carry only. The first stage C naught, the initial carry only I am considering for my all combinational circuits, and my output of my combinational circuit CC1 is C1 and CC2 is C2 and CC3 is C3. And here also for CC1 I am taking A0 B0, and for CC2 A0 B0, which is already available, and A1 B1 is a present stage input. Okay, A0 B0 is present available, A1 B1 is also already available, and A2 B2 is a present stage. So here you can see there is no dependency between the different stages of the different stages. Okay, so this is how the carry look ahead adder look like. Now let us analyze the equation of this combination circuit, the Boolean expression, how we are getting. So let us first draw the truth table for this particular carry look ahead error, and next try to analyze how we are getting this particular. Now let us draw the truth table of our full adder. These are our inputs A, B, C, and my let's take carry here and sum here. So we have 8 number of combinations: 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so here we will get no carry. Here also we will not get a carry. Here also will not get a carry. Here we will get a carry, and here also will not get a carry. Here we will get a carry. Here also will get a carry. Here also will get a carry. Okay, so in this all cases, if you observe carefully, so this is one group. When my A and B are equal to 0, let us make it as a group. And when A and B are equal to 0, 1, let us make this as a group. And A and B as 1, 0, this is make it one group, and this is another group. Okay, now if you observe carefully, whenever my A and B are 0, 1, my carry is being propagated. That is, 0 is being transferred simply to 0, or 1 is being simply transferred as 1. And if E and B are 1, 0, my 0 is being simply propagated to the output. Input carry is propagated as output carry, and input 1 is propagated as output carry 1. Okay, so I'll write it here. So whenever my A and B is equal to, okay, whenever my A is equal to 1 or B is equal to 1, I will write it clearly. A is equal to 1 or B is equal to 1. Whenever A is equal to 1 or B is equal to 1, my C in is equal to C out. That is, input carry is being propagated as output carry. So this is nothing but propagation is happening. Here in this particular case, propagation is happening. In this particular case, the input carry is being propagated as output carry. That's it. Whenever my A is equal to 1 and B is equal to 1, my carry is being propagated. So how can you write the equation for propagation? So carry propagation, let us denote it with Pi. So carry propagation Pi is nothing but A XOR B. Okay. So carry propagation will be equal to 1 whenever my A is equal to 1 or B is equal to 1. That is, carry will be propagated. Input carry will be propagated as output carry. And if you observe carefully, here whenever my A is equal to 1 or and B is equal to 1, whenever my A is equal to 1 as well as my B is equal to 1, then only my carry is being generated. Here you can see the input initially the carry was 0, output carry is 1. Input carry is 1, output carry is 1. Here in this particular case, whenever my A is equal to 1 and B is also equal to 1, then my carry is generated. Carry is generated. Okay, so whenever my a is equal to 1 as well as my b is equal to 1, my carry will be generated. So how can you write the equation for generate? Gi is equal to a and b. So this is the equation for carry generate. Okay, so this is how the carry will be generated. Now let us try to see the output sum and carry equations. So sum at each stage, okay, is represented by Si, where I is the particular stage. I represents the stage. Okay, so if I is equal to 0, it means first stage, and if I is equal to 1, it represents second stage, like this. So the equation for Si is nothing but Pi, which is carry propagate, XOR with Gi, which is carry generate. Okay, the sum will be produced if carry propagate is equal to 1, XOR with carry generate. So this equation we have for output sum, and for output carry generation we have Ci plus 1, which is nothing but Ci into Pi plus Gi. Okay, so this is the equation for output carry generate. Ci plus 1, which is nothing but Ci into Pi plus Gi. Gi is carry generate and Pi is carry propagate. And here you can see we are starting with Ci plus 1, that is we are not taking the output carry. So here if I is equal to 0, we are calculating the second C1, that is input to the second stage. Input to the second stage, that is C1, which is nothing but C0 into P0 plus G0. C0 is nothing but initial carry. Okay, C0 is nothing but initial carry. So if I so like this, I will get the carry equation for my C1, which is nothing but input to the second stage. Now if I want, if I is equal to, let's say I is equal to 0, that means C1 we are getting, which means output of our first stage, or you can say input to our second stage. Now if I is equal to 1, we will get C2, which means output of our second stage or input to our third stage. That is nothing but C2 is equal to C1 into P1 plus G1. Okay, and from the previous equation, you can write the equation for C1 as C2 is equal to C0 into P0 plus G0 into P1 plus G1. Okay, so this is the equation we can write for our second stage carry. Okay, or you can say the input for our third stage. Okay, and similarly you can write the equation for when I is equal to 2, we can write C1, sorry, C3, which is nothing but C2P2 plus G2. Okay, so we can write it and we can substitute the value C0 P0 plus G0 into P1 plus G1 plus G2. And in the equation for C2 also, you can observe there is no dependency upon the any stage carry also. Okay, the equation for P1 you already know. P1 is nothing but A1 XOR with B1, and G0 you already know, A0 into B0, sorry, G0, and G1 already know, A1 into B1. So there is no dependency upon the previous stage carry at all. So from this equation it's clear that there is no dependency upon the previous stage carry at all. Okay, so using this particular equations, you can draw the combinational logic circuit for this black boxes. So this combinational logic circuit, you can draw it. Okay, for generating C1, you can draw the combinational logic. Okay, here this logic you can draw C0 into P0 plus G0. You can for generating C1, we can draw the combinational logic for generating the C1. We can use one AND gate, and we can use one OR gate, which consists of one G0, C0, P0 and G0. Okay, So like this we can connect, and we can connect this. So this is the black box logic diagram for this particular black box, that is generation of C1. And from the equation also it's very clear that there is no dependency upon the previous stage carriage. There is only dependency upon the present inputs. That's all. So this reduces the propagation delay which was encountered in the ripple carry adder. Okay. Yeah. So that's all for this video. So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for tuning in.